We hung out somewhere. It was at Sammy's. Yes, that time.
Okay, now we're ready. So we're gonna start by graphing all of our constraints. So the first two are ready to graph. So if you're gonna graph x is greater than 0, remember that is just a vertical line on the y-axis where x is 0. And if I want to shade in the direction where all of the x's are greater than 0, am I shading to the right or to the left? To the right, thank you. So I'm just putting reminder arrows for myself because it would be quite a pain to shade this whole region and then shade it again and again and again as we add all of our other lines. Okay, y is greater than or equal to 0. That is just a horizontal line, basically your x-axis. I want to shade where the y's are greater than, so that would be above this line. Okay, great. Now, these other ones, I don't have them in y equals mx plus b form yet, so I'm going to take a minute and get them there. So this first one, we're going to minus that 2x over, and then I got to divide everybody by 3. So I didn't leave myself a ton of room, so I'm going to do it down here. So I'd have 3y greater than or equal to a negative 2x plus 6. Now we're going to divide everybody by 3. So that first one, rewritten in slope-intercept form, is there. We already did the second one. We had done that one together yesterday. So I already have the second one. I'll just rewrite it here so I have them all together. Y is greater than or equal to 3/2 x minus 4.5. And then the third one, let's minus the x over. So I'd have a negative x plus 20 and then divide everybody by 5. So I got y is less than or equal to a negative 1/5 x plus 4. Okay, so here are my 3. I'm going to put a box around them so I can find them again. I need to graph all 3 of these on this same graph that I have, right? All right, let's see. So this one, start at 2. Remember, I told you guys this yesterday. These are not negatives. It's just the other side of the graph. So that's just a positive 1, 2, 3. Sorry. Okay, those are all positives. All right, so we're starting at a positive 2, and I need to follow my slope down 2 over 3. Everybody's going to get connected with what? A solid line or a dotted line? Solid. They're all solid. Now, for this particular one, which way am I shading? Above or below? I've graphed this one right here. So where does this tell me to shade? Above or below? Above. If y is greater than, you're shading up. Where are the y's greater? Up, right? Y's increase above. So my little reminder arrows are going to be above this line. Okay, cool. This middle one, a lot of you were asking me, well, how am I supposed to graph this? Because I don't have a negative 4.5 on my graph. You're right, but you can graph it other ways. If I don't have a negative 4.5 on my grid, which I don't, one easy thing to do is to go back to the original and then just graph it like you were doing intercepts. Remember plugging in 0 for x and 0 for y? So if I plug in 0 for y, for example, that means x is just going to be 3, isn't it? Because you'd have 3x equals 9, or, pretend it's equals for a minute. So you get x has to be 3. That means I know one of my points, 3, 0, right? If I plug in 0 for y, I got out 3 for x. So that's a point on my line. And now I can just follow the slope that I have, which is where? Right here, 3/2. So if this is a point on my line and I know the slope is 3/2, then from this point, I can go up 3 over 2. And furthermore, when I connect these dots, doesn't it look like if I were able to zoom out on this grid, wouldn't this, if this kept going down, 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 doesn't it look like it could cross at negative 4.5? Yeah, which is where it was supposed to. So I'm feeling good about this one. Now I put my pencil on the line. I go right here And I ask myself, okay, should I shade above or below? It says y is greater than, so I'm shading above again. So I want to be above this line. Okay, and then I have to grab one final one right here. And this one is easy enough to do. I start at +4 and I'm going to go down 1/5, which runs me right into that. Connect these dots. Now for this line, where should I shade? Here's what it says, y is less than. So I'm going to shade below, exactly. So I go to that line and I want to shade below it. So in this case, the one region that works for all of my lines happens to be this funky quadrilateral in the middle there. Do you agree? It adheres to all of my my reminder arrows. So it's everything in here. So this one has 4 definite vertices or corners. And that's what I'm concerned about now. By the way, what happens if your lines don't cross at a nice lattice point and you're not sure where that coordinate is? I'm going to give you another. Remember how like when we were solving systems in 3 variables and I was like, hey, they're always going to come out to be an integer, even though in real life it could end up being wherever. Same thing. When we're doing these, they're pretty much always going to cross at a lattice point. So if they're not, something's probably wrong. Could they cross anywhere in real life? Sure. But when we're doing them, I need them to cross at nice lattice points because I need you to know where those locations are. Plug them in to the objective function. Now, in real life, though, if they don't cross, how would you find that point? You guys know how to solve systems. So you could just take the equations and solve the system algebraically. I don't find it that way. But for our purposes, they should always cross at nice spots. Wink, wink, bad at winking. You get the idea. All right. So there's half the battle. I have my feasible region. Remember, that's what we call this. So this is all the combinations, I should say, of things that would work within the given constraints. But now the whole point of this is to figure out, if we read the question that I drew all over, what values minimize the objective function. So in this case, I'm trying to, this is probably representing a cost. I want to figure out, all right, well, for my business, should I produce more jeans or t-shirts? Which is going to cost me the least? Or whatever the situation is, right? So that's where the objective function comes into play. So it's really only in the second half of the problem that I even care about this. So now I'm going to grab this and I'm going to look at my 4 vertices. Okay, in this case, I have 4. It could be however many. And so I just list them. So here I've got, in any order, it doesn't really matter. That one's at 0,4. I've got another one at 0,2. This one's at, where are you? 3,0. And one last one is at 5,3. So there's my 4 vertices. I'm going to grab that objective function. I'll just write it up above. Z equals 4x plus 3y. So for each of these, I'm going to do 4x plus 3y and see what values I get. So this one would just be 0 plus 12. This one is 0 plus 6. This one would be 12 plus 0. And this one would be 20 plus 9, 29. Right? So if I'm trying to minimize, that means this would be my best bet. Right? If I was trying to maximize, obviously I would have taken the highest one. Does that make sense? You with me? Okay. So then I would just, normally it's some kind of a word problem. So then you would give a sentence and say, oh, you should make, 2 pairs of pants and 3 shirts. But this is just numbers. So I might say something like 0 to minimizes the function. Okay. So far, so good? Does this make sense now? So if you got the shape wrong on the homework, do you see where you went wrong? Is everybody okay to graph and shade? Because now we're gonna add another layer, which is where we come up with these inequalities from just a problem that they give us. And we figure out what the constraints are and what the objective function will be. They might not give it to us. We have to find it. You ready? Does anybody have any questions right now? So far, so good? All right. So let me see if I want to, yeah. I might not go in order, but I think the next one is a good one to start off with. All right, so let's read the situation. They give us a problem up at the top here. So I'll just read it aloud, but hopefully you have your sheet in front of you. All right, it says, the area of a parking lot is 600 square meters. A car requires 6 square meters and a bus requires 30 square meters of space. The lot can handle a maximum of 60 vehicles. If a car pays $3 and a bus pays $8 to park in the lot, determine the number of each vehicle allowed in to maximize the amount collected. Do any of you live in Brimfield and like offer up your yard as parking? Do any of you do that? No, but you do?
No, we just lock our garage because like stuff has gotten stolen.
Really?
Yeah, they like people are stealing stuff all across.
Has it? You do?
Well, I used to a lot more. My uncle lives right near the church, so I wasn't working.
Oh my God. And so as soon as I read this problem, I'm like, this is Brimfield parking lot, right? Because you just set the scene, imagine it in your brain. Imagine that you're, because you know what I'm talking about, right? When this flea market comes in and they, you know, you could just park wherever, but people like sell spaces if they live nearby. They're like, hey, yeah, you can park on my lawn, but you're going to pay me $10 or whatever it is. So imagine that you had a space near this and you're like, okay, I can charge these people, you know, if they are in a car, I'll charge them $3. If they're in a bus, I'll charge them $8 or whatever, you know, whatever you have it set up as. Then you're like, well, I want to maximize my money. So should I just let in all buses? Should I just do all cars? What's the, you know, what's the mix? What's going to make me the most amount of money? Oh, I'm so excited about this one. And you could imagine like maybe there's like a town rule that's like you can only have a maximum of 60 vehicles. Is that what it says? Yeah, 60 vehicles, whatever. So just imagine that these are the constraints. So I can't just have, I don't have an infinite amount of space, right? I only have as much space as my yard provides. So let's assume it's 600 square meters. There's some rule that I can only have 60 vehicles on my yard at a time. Okay, cool. So that's another constraint. I can only have a maximum of 60 vehicles. I only have 600 square meters to begin with. So, oh, and also, could I have negative cars? No. So I'm not going to have negative cars or buses. So I need to take that into consideration too. All right. So do you understand the problem? Everybody's has their mind wrapped around what's going on here. We only have 600 square feet. I'm trying to figure out what's the mix that's going to make me the most money at the end of the day. All right, so first thing we need to do is assign some variables. So why don't we have X represent the number of cars and Y can be the number of buses. So now what we need to do is we need to think about all the constraints that are upon us, because we have a couple of different things going on. There's only so many numbers that I'm allowed to have in the lot, right? It says the lot can handle a maximum of 60 vehicles. So I'm only allowed 60 vehicles for whatever reason. So can anyone give me, using X and Y, some inequality that would represent that the number of vehicles total can't be more than 60? How would you write that as an inequality? Go ahead, Jeff.
X is less than or equal to 60.
You're halfway there. That would just be the number of cars. I need the total number of vehicles altogether. So Sam, how do you want to tweak it?
Would it be X plus Y is less than or equal to 60?
You got it. So the number of cars plus the number of buses together has to be less than or equal to 60. Right? Because I'm only allowed a maximum of 60 vehicles on the premises for whatever reason. Okay? So does that make sense? Is that inequality? Is that all right? Okay, now, well, that's great, but I also only have 600 square meters to deal with. So I can only divvy that up so many different ways. So I need to consider the total area of the lot as another constraint. I don't have an unlimited number of, amount of area. If I did, I would get all buses, right? Because they're worth more money, but I don't have enough space probably to just have all buses. So can anybody think of an inequality that would represent all the area that I can use up? Zach, go ahead.
6x plus 30y is less than 600.
That is perfect. Great question. If we look back up at the problem, see right here, it says a car requires 6 square meters and a bus requires 30 square meters of space.
Oh,
So for every car, they're going to use up 6 of the square meters that I have. I only have 600 to play with. So every car is going to use up 6 of those. How many cars will I have? X. So I'm going to do 6 times X. This represents all of the space that's going to get used up by a car, or all the cars that I end up with, right? Because it'll be 6 square meters times however many total cars I have. So that's all the area getting eaten up by cars. And then this chunk represents all of the area eaten up by buses, because each one requires 30 square meters, and I'm going to have Y of them. So 30 times Y is going to get me all the square meters all together that are going to get eaten up by buses. So all the square meters of both types of vehicles together can't exceed 600, because that's all I have to deal with. Does that make sense? Everybody's okay so far? All right, so there's those constraints. And then we mentioned this, just logistically, I can't have negative vehicles. So I am not going to allow the X's to go, oops, I did that the wrong way. The X's have to be positive and the Y's have to be positive. So there's my list of constraints. There they all are. I can now turn those into a graph, and I can graph the feasible region. And that feasible region will show me all of the combinations possible of these 2 different types of vehicles to park in this lot. I know, isn't this cool? I thought you would like this. So, all right, let's go ahead and graph. So I'm actually going to start with the X and Y, because they're these 2, they're the easiest to graph. So if I look at my grid down here, I have all of my X's need to be positive. So I'm going to start with solid line here. All of my X's need to be greater than or equal to 0, right? Same thing for the Y's. All of the Y's need to be greater than or equal to 0. Okay, those 2 are easy enough. Now, let's go back up to my other 2 constraints. Get those written in Y because I'm supposed to be form. All right, so this one I'm just going to minus the X over. So I'd have Y is less than or equal to negative X plus 60. And I might as well do this one too while I'm here. So let's minus the 6X over. And divide by 30. Okay, so if I'm gonna grab that top one there, I'm gonna start at a positive 60 and then my slope is a -1. So let's just take a look at our scale real quick. Start at a positive 60. Okay, that's fine. Just always keep in mind what's going on with your scale. I'm going 20, 40, 60. So each of my thick lines is 20, but it's the same on both sides. Okay, so if I need to do a slope of -1, if I go down 1 over 1, these little boxes, or down 1 big box over 1 big box, it doesn't matter because the scales are the same. If the scales are not the same, I have to be a little bit more careful and watch what I'm doing. But here the scales are the same, so I'm just going down 1 over 1. I'm just going to do the big boxes because they're easy. And where does that land me here? So everybody's a solid line, right? Yeah. So solid line. Hello. Oh my, thank you. Okay, can I have Maddie, Jack, Nate, and Tom? There you are. There you are. You're welcome. Thanks. Okay, so, oh, I didn't draw the line yet. Whoopsie doodles. Okay, so for this line that I just drew, right, that's this top one here, where am I shading? Above or below, according to this? Below. Why is less than? Why is less than down below? So I'm going to give myself little reminder arrows. Hey, you want to be below this line? Okay, great. And I just have one more to grab. Let's see. So that one starts at 20. And I want to go down 1 over 5. I can't do it on the big boxes because I'm going to run out of space, but I can do it on the little boxes because my scale is the same. Down 1 over 5. Oh, is that 5? Oh, it's 4. Oops. Down 1 over 5. Down 1 over 1, 2, 3, 4, 5. Ooh, a nice intersection point. Oh, go figure. Down 1 over 1, 2, 3, 4. One more right there. Okay, draw that line. So for this line that I just drew, I got to ask myself, where am I shading, above or below? So I go back here, right there. And this tells me I'm going to shade below because y is less than. So I want to be below that line that I just drew. So the one region that works for everybody is just this one in here. Does that make sense? And you know what? I'm also going to label our axes here. We said X was the number of cars. So these are cars on this side, and this was buses. So this represents all the different combinations possible, right? So I could have no cars, 20 buses. I could have no buses, 60 cars if I wanted. Or I could have any combination. So these, all the dots that are on the inside here would just represent, they're still possible, but maybe I'm not, maybe I haven't filled the whole lot, right? It's possible for me to have 1 car and 1 bus. It's a possibility. It's not going to make me the most money, but if it's a slow day, maybe there's just not enough. But this represents all the different combinations of buses and cars that I could actually have given my constraints. Does that make sense? So I could ask myself, well, hey, is it possible to have 20 cars and 20 buses? No, because 2020 is not in my feasible region. Isn't that interesting? So anywho, there's the first half of the problem, is getting all this done. Now I want to figure out, well, this is all fine and good, but I want to make some money, honey. Where am I going to get the most money? Which combination is going to get me there? We're assuming, I mean, if you take a look on the best Brimfield day, there's no shortage of cars, right? So we're assuming you'll have plenty of cars to choose from, but you want to maximize. Let's see what you're gonna do. So, oh, we didn't write our objective function yet. We need to do that. They didn't give us one. So let's read what it says about the objective function right here. Got a little blurb. So objective function, this is an equation that models whatever it is you are trying to maximize or minimize. Usually that is either the profit to be made, which we would want to maximize, or the cost, which we would minimize. In this case, we want to maximize the profit to be made. So can you read the information given to us and think about what the objective function would be? If we're trying to model profit here, go back and read the problem. Can you come up with, Zach, you got one? Go for it.
Z equals 3x plus a1.
I love it. If you go back and you look, didn't it tell us all the way back up here? Cars are going to give me $3 each. So I'm going to get $3 from every car that pulls in. So I'm going to do $3 times X. I don't know how many cars I'm going to end up with, but I'm going to get $3 from each of them. Then I'm going to get $8 from every bus. So that's going to be 8 times Y, the number of buses that come in. Those two values together, $3 from every car and $8 from every bus, that's going to be my profit. Does that make sense? So I'm going to use a P for profit. You can use a Z if you want. But we have $3 for every car and $8 for every bus. Is everybody okay with where that came from? Does that make sense? All right, now we're ready to go. We're going to take our 4 vertices. 0, 20 is one of them. I do have one at 0, 0, but do I care about that one? Now be careful. What's our scale in here? 5 5s? Yeah, 45, 50, 55. Yeah, so this would be at 50, 10. We've got our objective function, 3x plus 8y, and we're going to see what combo am I going to go with. Ooh, exciting. Obviously, I don't care about 0, 0 because that's not, I wouldn't make any money there. So that one's kind of irrelevant. Hmm, 180 if I go that route. And let's see this mix up. That's 150 and 80 is 230. Oh, sorry. A little bit off. There we have it. So now I'm trying to maximize this. So clearly this is my maximum. So what does that mean? If you had to write a sentence answering the question, what would it be? How many cars should I have? 50, right? Remember, we said that X was cars. So I should have 50 cars and 10 buses. Park to maximize profit. How about that? Isn't that something? Yes.
Wait, where did you get the like the equation, like the x plus y again?
So we had to come up with that. And we want to maximize our profit, right? So I need to ask myself, well, how much money am I actually making from these things? So if you go back to the
Oh, I see
original
it.
question.
Reasoning. Okay.
Yeah.
Thank you.
So that one almost, oh, your objective function is almost always going to deal with money, either costs or profits. So the money portion of the problem usually just ties right into that objective function. So how do we feel? It's kind of interesting, right? I like these ones because you can kind of, I don't know, you can envision this. Hopefully. Should we try another? I thought you'd never ask. Oh, let's flip the page. Let's see what's next. Let me see if this is the one I want to do next. Yeah, we can do this one. All right. Okay, new situation. You ready? So I'll help you get started and then I'll let you do a little bit more of it on your own. So this time we are manufacturing ski clothing. We have ski pants and ski jackets. All right, so we're in the ski clothing industry. The profit on a pair of ski pants is $2. Why are you bothering? But anyway, on a jacket is $1.50. Okay. Both pants and jackets require the work of sewing operators and cutters. There are 60 minutes of sewing operator time and 48 minutes of cutter time available. It takes 8 minutes to sew one pair of ski pants and 4 minutes to sew a jacket. Cutters take 4 minutes on pants and 8 minutes on a jacket. Find the maximum profit and the amount of pants and jackets to maximize the profit. All right, so let's break it down piece by piece. It's really not so bad once you get the hang of it. You just gotta get used to it. So they already said X is gonna be ski pants and Y is jackets, all right? So they did that part for us. And they're saying there cannot be negative pants or jackets, right? Two inequalities to represent that situation. So everybody go ahead and answer A. Our first restriction is that we can't have negative pants or jackets. Pants is X, jackets is Y. Okay, everybody got that? So hopefully you wrote X has to be greater than or equal to 0 and Y has to be greater than or equal to 0. There's our first two constraints. Agree so far? All right, cool. The next one says, express the cutter's time to make pants and jackets as an inequality. So let's go back and read about the cutters. So let's see. All right. So it says right here, there are 60 minutes of sewing operator time. I don't care about that right now, but I care about this. There's 48 minutes of cutter time available. So I only have 48 minutes for the fabric cutters to work with. There's only 48 minutes. So now I'm like, okay, I only have these 48 minutes and I want them to cut for me pants and jackets. So if we keep reading, it takes 8 minutes to sew. I don't care about sewing. Oh, right here. It takes 4 minutes. Oh, that's sewing still. Sorry. I got to read this next. Here it is. Cutters take 4 minutes on pants and 8 minutes on a jacket. So just focusing on the cutting of the fabric right now. Jimmy.
I wrote that.
Oh, I thought you had an inequality for me.
I can. Plus 4y equals 60.
I think you're doing the sewing. You're right for the sewing, but not the cutting.
Oh,
I'm on the cutting. I don't know why they did cutters before sewers, because you're right that they talk about sewers first, but
4x plus 8y equals 48.
you're close, yes. So it's got to be an inequality though. So where is this coming from? Cutters take 4 minutes on pants. So that's going to be 4x. they're gonna use 8 minutes on a jacket, so that's 8Y. The time that they're spending, they only have 48 minutes to deal with. So I can't say equals 48. It can be less than or equal to 48. Go ahead. But before we continue, do you understand where this came from? You got to get used to just pulling out the pieces of the information that you care about. Go ahead and everybody try the sewing one now. We just did the cutting one. So it's the same idea for the sewing. So go back and read. All right, well, how much sewing time do I have? And how much time does it take to sew the pants and the jacket? So see if you can write the sewing inequality. Do any of you sew? You do? You do? I sew a little bit. I don't ever really make anything that great. I made scarves. I have an embroidery machine, but I never use it. I should get back into it. Who has the time? Anyway. All right. Who thinks they have the sewing inequality? Angelina, go for it.
8x plus 4y is less than 32. Or less than 32.
I agree. If you go back, there were 60 total minutes of sewing time available. And then, let's see, here's the one where the sentence where they're talking about sewing. 8 minutes for pants, 4 for jackets. So there it is. Okay. So far, are we all right? I think we have covered all of the constraints. They have us writing the objective function right here, so we might as well. So write an equation for the anticipated profit. So I'm going to use P for profit. So go back and read and see if you can figure out, well, how much money am I making off of these things? Nathan, you got it? You got it. If we go all the way back, the second sentence says the profit on a pair of pants is $2, the jacket is $1.50. So I'm going to make $2 times however many pants that I create. And I'm going to do $1.50 times however many jackets I end up making. So there's my objective function. And now we know what to do. I have all my constraints. I just have to graph them, take those vertices, pop them in. So I think I did, when I did this one, I think I just did a scale of every line was 1 and it fit just fine. I think there's 20 all the way across. Yep. So if you just do every square is 1 box, it should be fine. I mean, you don't have to, you can do whatever scale you want, but. Okay, so take a moment, everybody go ahead and graph these. I'm gonna graph it too, and we'll see if we end up with the same image before we move on to the next part. I'm gonna go up and take a moment and rewrite my inequalities in slope-intercept form. Okay. I don't know if you're done yet, but I'm going to wait for you to shade in the one region that works for everybody. Hopefully, your lines look something like mine. Bless you. So I'm trying to represent my 3 regions that I have with 3 different colors. Which one should be the one that I'm shading in? The purple area, the yellow area, or the green area? The yellow is correct because I need to be below both of these lines, but above these, right? So it should just be this little region right here. And there we have it. So this shows me all of the different possibilities of jackets and pants that I could have made given the constraints that I'm dealing with. Those are all the combinations. Yes, Jack. Oh. Wait like 2 minutes, because there's a very important thing, though, piece of the conversation that we have to have. Okay. So also, let me label my 2 sides. X was pants, right? So we have pants on this axis and jackets on the side. So these are all of my different combinations, right? Now, here's where we have a little bit of a weird thing happening with this particular problem. If I go and I take a look at all of my corner points, my vertices, right? Yeah, I got 0, 0. I don't really care about that one because it's never going to give me the maximum of anything. So whatever. Here I've got 0, 5. Here, let's see, that would be at 6, 3. Is that right there? This one that I'm talking about? That's 6, 3. And then now this is interesting because you've got one more right there. And that one, I know I said that they would always be at a lattice point. I kind of, well, that was, I guess, a little bit of a fit, but I meant like where the 2 lines cross should always be at a nice point. This is hitting in between, what is this? 5, 6, 7. So that's at a point, that's 7.5, right? However, remember what I'm talking about, pants. Can you sell 7.5 pants? No. So since this is a real problem, I can't logistically sell 7.5 pants. I could make 7.5 pants, right? If I work in a factory, I could make half a pair of pants and then, oh, time for lunch, I'm leaving, right? You can come back and finish the job, but I can't sell half a pair of pants. I guess you could, they're shorts, but anyway, you get what I'm saying. So this point right here doesn't make sense, but this one right here does. I could certainly sell 7 whole pants. So I'm going to go with the closest point that has whole numbers right near that intersection point. Does that make sense? Right? Because I can't sell half a pair of pants. So I would consider the point, what did I say, 7, 0? Because it is certainly within my feasible region, but the very end of my feasible region doesn't make sense in this real world problem. You with me? Yes. 0. Yep. Oh, you're saying you could do 7, 1.
Yeah.
Oh, yeah. Oh, I like that. Yeah, why not? You're right. That would give me a better shot, and that's definitely within my realm of possibility. All right, let's see what we get. So our profit was 2x plus 1.5y, right? Let's see. Oh, I didn't realize I was off for that, but there you have it. Did you get what I got? Jackie, can go. if you want. I figured as much. So does this make sense? Did you get what I got? Yeah, everybody agrees? So now I'm looking, I'm trying to make the most money, right? So there it is. That's the combo I want to go with. So they're asking in part G, they want to know what is that maximum profit? Looks like it's going to be $16.50. And how many ski pants and jackets that was, so just make sure we're matching them up. X was what, pants? So I should have 6 pants and 3 jackets, we said. So how are we feeling about linear programming? It's kind of neat, right? Different, a little bit. Okay, so what? Whoa. Just throwing things around today. Let's see. Oh, there's only 2 left. Why don't we have those 2 as the homework? I'll help you, maybe why don't I let you try them? Feel free to work together. I have the keys here, so if you want me to, even if before you make your graphs, if you just want me to check your constraints, I can do that. So these ones, well, I'll help you a little bit with the first one if you want to listen. If you don't want to listen, that's okay. If you just want, you're like, I just want to try it on my own. Because these ones, I don't have it broken down into as many steps. So you're kind of more on your own here, but I'll help you a little bit. So this one says we are baking a tray of corn muffins and bran muffins, okay? So we've got corn muffins, which use 4 cups of milk and 3 cups of wheat. Bran muffins, 2 cups of milk, 3 cups of wheat flour. Now, I think wheat and wheat flour is the same thing. Yeah, so just add the word flour there. Sorry, it's all the same. Okay. And he makes $3 per tray of corn muffins, $2 per tray of bran muffins. How many trays of each type of muffin should the baker make to maximize his profit? Okay, so first thing you have to consider is what are the constraints? Let's start with the easy one. Can you have negative muffins? No. Oh, actually, so let's start. Let's all have X and Y be the same thing. So let's have X be corn muffins. And Y is going to be the number of bran. Bran muffins? Ugh. Sorry if you like them. All right, so can they be negative? No. So our first set of constraints is to not let X or Y go negative. So X has to be positive, Y has to be positive. Okay, great. You're going to have 2 other constraints here. You only have so much milk and you only have so much wheat flour. That's what you have. You walk into your bakery, you're this baker, you're like, oh, wow, I only have 16 cups of milk and 15 cups of wheat flour. I better figure out what I'm gonna make to maximize my profit here. So one of your constraints will be based off of milk. One of them will be off of this wheat flour. Does that make sense? So you gotta look, I'll help you with the milk one, but then you'll be on your own with the wheat flour. I know I tell you I gotta let you do it, and then I just do it all. I gotta stop, right? I'll just do the one, just the one, and then I will stop, I promise. All right, milk. And I won't even do it, you'll do it. So can someone tell me what the inequality would look like for the milk? Jeff, go ahead.
Would it be like 4x plus 2y is less than 216?
Yes, that's perfect. If you go back and you read the question, if I'm just focusing on milk, forget the wheat flour for a minute. Read about milk. Oh, 4 cups of milk right there. 2 cups of milk right there. The baker has 16 cups of milk. There's the pieces that I care about. All right, so all my corn muffins are going to use 4 cups of milk. So those are X, so 4X. That's all of the milk I'm going to use up in the corn muffins. Add to that, then I keep reading, oh, bran muffins. Those things are going to use up 2 cups of milk. So 2 cups of milk for every tray of my bran muffins. And then if you keep reading, I only have 16 cups to work with. So those 2 things together cannot exceed, so they have to be less than or equal to the 16 total cups that I have. So there is your milk inequality. Now you go back and you do the same thing for the wheat flour. You're like, I don't have unlimited amounts of wheat flour. I only have however much it says. Each different type is going to use up however much it says. So you come up with that second inequality representing the wheat flour. Once you have all of that, you can either graph it and worry about the objective function later, or you can write your objective function now. It really doesn't matter. And then you know what to do from there. Okay, so I really am going to stop, let you try it. And again, I have a key, so if you want me to check any of it, let me know. Feel free to work together if you want to.
Example like this, where everybody can see what's possible.
Everybody should get the same.
So it's just be corn. Okay.
Sure. 9 plus 4. Okay. Yes.
I like those equations, right?
Let's see. -2x plus 8.
Yeah, like,
Correct. And this one would be -x plus 5.
oh yeah. So yeah.
Yes. But they're not equal.
Oh yeah. It's doing the same.
It could be,
Oh yeah, but that always has to be greater.
yes.
That is that.
Yes.
This second one is
Right, only the very corners of your shape.
Oh.
Okay, I'll be right over there. Yes. And yes. Oh, sure. Like that. Yes. Yes.
It's like.
What do you tell?
Huh?
Yeah. Stop this. I'll be right over there. Or maybe. Let me pause this. How do I? There we go.